In many cases, the eigenvalue eigenvector information contained within a matrix A can be displayed in a useful factorization of the form A equals P times D times P inverse, where D is a diagonal matrix. In this section, the factorization enables us to compute A to the K power quickly for large values of K, a fundamental idea in several applications of linear algebra. First example, if D is equal to 5003, then D squared is D times D, which is the multiplication of those two matrices together. You are more than welcome to use your calculator to multiply these. If you use your calculator, you'll find the main diagonal will contain a 25 and a 9, but just to show the powers and how they are related, I wrote these as 5 squared and 3 squared, which happens to be the main diagonal squared. D cubed is 3 D's matrices multiplied together. I went ahead and saved this D squared because D times D squared is D cubed. If you go through the multiplication using a calculator, you will wind up with 125 and 27 on your main diagonal. But in exponential form, that is 5 cubed and 3 cubed. So basically, for this one, you maintain your main diagonal with whatever power you're multiplying, squares or cubes. So in general, D to some numerical power 1 or greater will be equal to 5 and 3 respectively to the K power on the main diagonal. If matrix A is equal to P times D times P inverse for some invertible matrix P and a diagonal matrix D, then A to the K is easy to compute. Let's look at another example. Let A be the matrix 7, -4, and 2, 1. Find a formula for A to the K. Given that A is equal to P times D times P inverse, where matrix P is this 2 by 2, and matrix D is the same diagonal from the first problem. First, use your calculator to invert matrix P, and that'll give you P inverse. If you do it by hand, just remember you need the determinant, which is -2 minus -1. That's -1. You swap places and change signs. If you don't want to mess with doing it by hand, it's totally appropriate to use your calculator. But this is P's inverse. Now, since matrix A was P times D times P inverse, we can go ahead and claim that A squared is going to be A times A. Since P is invertible and using the associative property, we can group P inverse and P together, and that's going to turn into an identity matrix. That leaves us with P times D times D times P inverse. Well, that's D squared. So A squared is equal to P diagonal squared times the inverse. If you move up to a cube, A times A squared, similar to what we did on the first example, you take matrix P, the square diagonal, A times A squared, so we're going to have matrix A, what we just found for A squared. Group all these together, you have P, D, P inverse, P, D squared, P inverse. That's a mouthful. Again, group the P inverse and P together. Those always multiply to the inverse as long as the identity matrix, These two will multiply to an identity matrix. That leaves us with P, D times D squared times P to the inverse, P inverse, leaving us with D cubed in the middle. So now we see the pattern. In general, A to the K is equal to P times your diagonal to the K power times your inverse. giving us, now if we take this expansion, that's P times diagonal to the K power times P inverse. So we have P D to the K and P inverse. And if you need to refer back to the other slide or pause the recording, totally understandable. Okay, so I'm going to multiply these two matrices in front together. 5 to the K times 1 plus 1 times 0, that's 5 to the K. Second row, first column, negative 1 times 5 to the K plus negative 2 times 0. Row 1, second column, 1 times 0 plus 1 times 3 to the K. Second row, second column, negative 1 times 0 plus negative 2 times 3 to the K. This is the matrix that's the result from the first two matrices up here multiplied. Now it's time to multiply by P inverse. 2 times 5 to the K plus negative 1 times 3 to the K. Be very careful not to call that a 10. Second row, first column, 2 times negative 5 to the K plus negative 1 times negative 2 times 3 to the K. Well, those two negatives, that's where this positive comes from. First row, second column, 5 to the K times 1 plus 3 to the K times negative 1. Another reminder, don't call that 2 to the K. Exponentials, you got to be careful. And then finally, row 2, column 2, negative 5 to the K times 1 plus negative 2 times 3 to the K times negative 1. There's a whole bunch of negatives in there, but those two make a positive. Be very careful. A quick note, a square matrix A is said to be diagonalizable. Yeah, that's a good one. If A is similar to a diagonal matrix. Now let's look at the diagonalization theorem. This one has quite a bit in it. In your e-text, it's on page 291. An n by n matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. If A is equal to P times D times P inverse, with D a diagonal matrix, if and only if the columns of P are n linearly independent eigenvectors of A. In this case, the diagonal entries of D, and we're going to go over an example of it, are eigenvalues of A that correspond to the eigenvectors in P. In other words, A is diagonalizable if and only if there are enough eigenvectors to form a basis of Rn. And this is called an eigenvector basis of Rn. Okay, so that's a lot to take in, a lot of words. For the example we're about to do, if you want to pause the video, grab some water, put your seatbelt on, put your tray tables in their locked and upright positions, because we're going to actually do a diagonalization, and there are a lot of steps, and it uses a lot of skills from 2 sections ago on your YouTube channel, 2 videos up from this one. So here we go. We're going to diagonalize matrix A if possible. At the end, I'll show you what would be the case of not being able to diagonalize one. So let's start with a 3 by 3 matrix. Excuse me. Matrix A is 1, negative 3, 3, 3, negative 5, 3, 3, negative 3, 1. The goal is to find an invertible matrix P and a diagonal matrix D such that this matrix given is equal to these 3 matrices product. Step 1, and this will be from your 5.1 section. The title of that section, it's 2 videos up, but anyway, the title of it is Eigenvectors and Eigenvalues. Our first step is to find the eigenvalues of A. That's where we create a matrix A minus lambda times the identity, matrix A minus lambda times the identity, subtract based on position. This is the matrix that you get after performing that operation. Once you get A minus lambda I formed, and it's this 3 by 3 matrix here, then we calculate the determinant of this 3 by 3 matrix. I'm going to go down the first column, so let's remember, you take your first or your upper left term, 1 minus lambda, and then you take the determinant of the remaining 4 terms not on the same row or column. Minus, you have to alternate signs, minus -3, and then ignoring that column and row, you have 3, 3, 3, and 1 minus lambda, plus 3, ignoring that column and row gives you these 4 entries, 3, 3, -5 minus lambda, and -3. Now, remember these vertical bars represent determinants, and so we're going to calculate determinants of a 2 by 2 matrix. So we have 1 minus lambda, multiply the main diagonal minus the other diagonal. Minus -3 is plus 3. And then we'll do the determinant of the second matrix. 3 times 1 minus lambda minus 3 times 3. Plus 3. Determinant is 3 times -3. I try not to do too much on a step so that you guys can see all the numbers and where they're placed. I do apologize for all the 3's. It just happened to be that way on this problem. So we have 3 times -3 minus 3 times -5 minus lambda. This is that first expansion. A lot of words. All right, now it's time for cleanup. 1 minus lambda, -5, +5 lambda minus 1 lambda. That's 4 lambda. Positive lambda squared. So I just basically FOIL and combine like terms. Minus -9 is +9. Then move to the second group, 3 times. Inside it's 3 minus 3 lambda minus 9. Third group, 3 times -9 plus 15 plus 3 lambda. Combining further, in the first bracket, we have lambda squared, 4 lambda, -5 plus 9 is 4. Inside here, we have 3. All right, so let's look at this, be very careful. We have 3 minus 9, that's -6. Times this outer 3 is -18, and then minus 9 lambda. In the third bracket, that's 6 times 3, that's 18, plus 9 lambda. We catch a break, these back 4 terms all zero each other out. So basically now it's 1 times these 3 terms, so we have lambda squared plus 4 lambda plus 4, and then redistribute with negative lambda. So negative lambda cubed minus 4 lambda squared minus 4 lambda, and that gives us these 6 terms. And then finally, in descending order and combining like terms, negative lambda cubed, 1 minus 4, that's negative 3 lambda squared, 4 lambda minus 4 lambda zeroes out, and plus 4. In your ebook, your e-text, when it goes over this, it's on page 292. Your e-text skips all this middle work. I don't like to skip a whole lot because it's just hard to remember 2 sections ago the exact steps you take. So anyway, I went ahead and worked out all these steps. Your e-text skips over it and actually just goes right to the eigenvalues. Now this is a little bit harder to factor than you would think because you have a cubic, a square, and then just a straight up constant. To get these eigenvalues, there's a little math hack you can use. If you were to take a graphing calculator and graph this characteristic equation, just pretend the lambdas are x's, you'll find that negative 2 and 1 are your x-intercepts. Those are your real eigenvalues. So that's one crazy step 1. This is step 1. Step 2, find 3 linearly independent eigenvectors of A. Now this is also something we did back in 5.1, which was the Eigenvectors and Eigenvalues video / homework section. One of our eigenvalues was 1, so we have A minus 1 times the identity, A minus 1 times the identity, or just A minus the identity. That's this 3 by 3 matrix. Now recall, to get eigenvectors, what we did was we would take that 3 by 3, in this case matrix, we'd add in a column, we'd augment with a column of zeros, row reduce, and we would look for free variables. Well, there's a pivot in columns 1 and 2, but not in the third column, so x3 is free. x1 is equal to positive, if you were to set this equal to 0 and carry it over, positive x sub 3. x2 is equal to negative x sub 3. And then x3 is free, so we just recopy it. Pull out the x3, and that leaves you with 1, negative 1, and 1. This vector is an eigenvector for the eigenvalue 1. So when lambda was 1, this was our eigenvector that corresponded to it. I'm going to call it V1. Switching to the other eigenvalue, which was negative 2, A minus negative 2 times the identity. Now, if you want to consolidate this and call this plus 2, that is totally appropriate. And then you would just do a plus sign in the middle, a big old plus sign, and put 2's here. Carry out this operation, and you get this wicked 3 by 3 matrix. I think the author is kind of sadistic putting all these 3's in a 3 by 3, but that's just how it worked out. Now, once you've formed your matrix from A minus lambda I, then you augment with a column of zeros, row reduce it. We only have one pivot column, so x1 is the only one that has a pivot. x2 and x3 are free, and I made a note of that here. x1, if you were to carry x2 and x3 over, they would both go negative. x2 and x3 are free, so those two are fairly easy to fill out. But just remember, when you augment with a column of zeros, it's like a pretend equals there. Factoring out an x2, or pulling it out, you have a negative 1, a 1, and a 0 for the x2's. For x3, you have negative 1, 0, and 1. These two eigenvectors I'm going to call V2 and V3. Now, it's very important here. If we don't get 3 eigenvectors, then this matrix in the beginning, matrix A, can't be diagonalized, 3 vectors are needed because A is a 3 by 3 matrix, and that's a critical step. If that fails, matrix A can't be diagonalized. Okay, the last 3 steps are not bad at all. If you can survive the first 2 steps, getting your eigenvalues and getting your eigenvectors, then it's all downhill from here. Matrix P, which is part of that A equals PD P inverse equation, you actually take all 3 of your eigenvectors that we found in step 2 and make each one a column of that matrix. Okay, so we first found an eigenvalue of 1, and it produced an eigenvector of 1, negative 1, 1. You want to keep these in order too. The eigenvalue of negative 2 produced 2 vectors, which form the basis, and those eigenvectors we called V2 and V3. Those are put in here, and you got to keep the order. So we had 1 and its eigenvector. Negative 2 produced 2 eigenvectors, and that was V2 and V3. Okay, now since A is supposed to equal P times D times P inverse, don't worry about finding the inverse. What we're going to do is we're going to right multiply both sides by P. So AP is going to be equal to PD, because if I put a P here, those will go away for the identity. This is what we have to check. So A from the original problem times P from our eigenvectors, this A times P here, equals P from the eigenvectors times D, which is a diagonal of the eigenvalues. If you multiply the left side and then multiply the right side, you get the same 3 by 3 matrix. An n by n matrix with n distinct eigenvalues is diagonalizable. This one that we just finished had only 2 eigenvalues, but lucky for us, the one that repeated, because remember when we did from the graph, the one that it was a clean cut through at 1, but there was a bounce at negative 2. Negative 2 was an eigenvalue that has an even multiplicity because of the bounce. You might remember that from college algebra or pre-cal. If a graph bounces on the x-axis, it has to have an even multiplicity. If it cleanly cuts through the x-axis, it has an odd multiplicity. So this eigenvalue of 1, it was a clean pass. That one eigenvalue had 1 eigenvector. At negative 2, the graph bounced off the x-axis, so that's why there's 2 of these. Negative 2 was an eigenvalue with a multiplicity of 2 because of the bounce. Anyway, lucky for us, negative 2 produced a V2 and a V3 eigenvector. So we had the appropriate number. If, say, we calculated the eigenvector with the eigenvalue with a minus negative 2i, but we only got 1 eigenvector, like there was only 1 free variable, then we wouldn't be able to finish the problem. So that's a fine line, and it's hard to understand it. It will take some practice, so when you guys I try to do my best to do a 4-day space on these assignments. This one, and I didn't put a whole lot in the homework. It's like 4 or 5 problems, something to that effect, because they are so long and time intensive. But as always, if you need any help, let me know. I'll be happy to try to help you out. You just got to, on the first two steps of diagonalization, you've just got to be super meticulous, double check your work every step. All right, so thank you, and it won't be long before the semester's over. We only have, let's see, after this video, maybe 5 or 6 sections left. But this one, when you get to this one, it'll be about the end of April for the or excuse me, the beginning of April, end of March for as far as the pacing of the class goes.